Okay, I think we should start. So this is the last seminar in the context of this year's course. And it's a seminar on AI in math and theoretical physics, status and prospects by Michael Douglas. Now, Mike is a star in theoretical physics and has a long-term interest in computing and computer science. So I think that no one was better qualified to address that topic than him. So thank you.
Thanks. Thanks for the generous invitation, Marc. Thanks to the Collège de France. Thanks everyone for coming. So this is a topic which, on some level, is hard to get away from these days. There are newspaper articles and developments, and I'm sure very likely all of you at this point have tried ChatGPT and the related models, and perhaps are using them. And just this year, I would say things really seem to have accelerated to the point where people like Sam Altman, the head of OpenAI, will openly say, we think that there'll be a computer which is, in some sense, as smart as a human in 2 to 3 years. And exactly what that means, of course, is very vague, and we'll discuss some of that in the talk. But it does mean that we have to really very seriously think about what this means for the way we work, for our field, for society, and so forth. And so there's well, let's see, this guy. This was working until a minute ago, so it's not a big deal because I can do this. But anyways, I'm sure, again, everyone here has followed the newspaper reports, the advances. Some fields have had huge impacts, some fields of science, and I think the most illustrative, the paradigmatic one, is structural biology. So protein folding, this 50, 60-year study of protein folding led to huge amounts of progress. And building on that, in 2021, 2022, DeepMind was able to, in a sense, solve the problem. So that's a case where it totally revolutionized the scientific field. And on the other hand, many fields, it's useful. I'll describe many uses of it in math more than theoretical physics, because it's sort of easier. There's a broader range of possibilities in math, but all the techniques equally can be used in theoretical physics. And I'll go through a variety of, again, interesting applications, discoveries, but I think it's fair to say hasn't revolutionized the work that we do. But the point to keep in mind, and this graph, I'm going to come back, this is the graph that will make the point in a quantitative way, is that the progress in computing and now the progress in AI is exponential. And that's not just a metaphor. There's a precise sense in which you can say it's exponential. And one precise sense will be very familiar, the Moore's law that has governed the size of a transistor, say, on a chip, the cost of computing per operation. And for many years, that was doubling at every 2 years, a very steady pace. And although that physical type of exponential increase has actually slowed down, many other things continue, and there does seem to be this broader Moore's law that has roughly a stable doubling of the compute available at a given cost every 2 years or so. So I'll come back to this graph and what all this means, but the red dots up in the top right are a quantitative measure of progress in AI. And this is a log scale on the y-axis, so you can again see an exponential improvement. This goes back to 2012 or so, this famous deep learning revolution. And this doubles every 2.5 to 3 years. So the point we'll make from that now is that given exponential growth, whatever you've seen so far is still just a preview for what could happen in the coming years, because it just continues to, the future the future scale of computing is available is much greater. Okay, so nevertheless, okay, what do people use it for in research, in pure math and theoretical physics? And well, again, there are valuable things you can do with it. And maybe I'll ask for a show of hands. How many people would, at this point, say, I use AI, a language model, even machine learning, we'll just say very broadly, in some important way in my recent work. Maybe not all the time, but it's been given an important contribution. Okay, there's one. How many people would say that? I mean, I can sort of say it, but not very many. And again, I'm sure many of you have tried. There's this use of finding patterns in data science. That's again, experimenters, observationalists have very much had to gotten great advantage from machine learning with their big data sets in many ways. One can use it for search, and I'll talk about that in a variety of senses of the word search. Perhaps the best use so far of these language models is for writing a computer code, and it's been widely reported how valuable. If you've tried coding, in fact, if you seriously code in your work, you probably are using at this point language models. They can be very valuable. But if you go back, and because AI has a long history. The ideas really date back to the 50s, and in the earlier days there were many ideas, proposals. How will AI help people? How will it help scientists? Well, you could have an AI research assistant that does, maybe perhaps the more well-defined, the more tedious aspects of research. Perhaps something more sophisticated, but in any case, a useful assistant. Really good search engine that you would say, here's a paper I've been looking at. Summarize it. Tell me all the subsequent papers that build on it in a useful way. And that starts to happen, if you, for example, used OpenAI's deep research. I'll come back to that. There's this field of interactive theorem proving that can take mathematical proofs and express them in a form which can be 100% verified by a computer. And AI should make that easy. There's, of course, the question, can a computer actually discover make its own discoveries in math and science? And really, these things either are just starting or have not happened in any significant way. And so, of course, one has to ask, well, is there some reason? Are these things in some fundamental way harder than what we see AI and computers doing now? And my guess, and I'll make a bit of this case in the talk, I have other talks that dwell more on this particular point, is there probably is no fundamental barrier, and these things will happen really over the coming few years. And that's the point which we'll explore in this talk. And the way that we'll do it is, we're basically extrapolating from the recent progress and this knowledge about how things are advancing. And so we have to start by surveying the situation now. And I'll go through a variety of areas in math and physics and quantitative science where people do use machine learning and AI and have gotten significant results in the discoveries using it. So there's, I'm surprised because this was working, but in any case, so there's machine learning for scientific computation. There's a topic of mathematical data science. There's search and optimization in computer terms, the interactive theorem proving. And so we'll review where we're at now. And having seen that, then to make this point that the exponential progress really will make many of these things take off, we can compare with history, and in particular computer chess was a very well studied and a subject where a problem where computers went from kind of okay, able to play chess masters in the mid-90s to superhuman ability over about a 10-year time period. And so that there's not just an analogy, but there's a quantitative analogy that I'll make that will suggest that we are starting a similar period for this. Again, it could be many applications, but in particular research in the mathematical sciences and physics and so forth. Okay, so before we get into as I said, the survey, I think I'm going to give a very brief review of machine learning from a more sort of theoretical math, theoretical physics point of view, trying to abstract the central things. And again, many of you, if you've taken any course on machine learning, this at some level will be familiar, but this will get us all on the same page. And a lot of the concepts can be described very concisely. So again, machine learning is not a new field. I would say it started in the 90s, and it combines methods. Statistics is kind of the core of it, but computational applied math. It takes ideas from physics, as we were, of course, reminded by last year's Nobel Prize, John Hopfield, and neuroscience and other areas. And a central aspect of machine learning is this idea of a parameterized function, some big class of functions from input space to an output space with so many adjustable parameters that in some sense, which we'll keep vague, you can approximate any function usefully well. And a very common and not the only, but perhaps the single most used version of this is the feed-forward neural network, where we take a input vector x, n-dimensional vector. We apply a matrix, a linear or an affine transformation, theta 0. Then we apply a nonlinear transformation, which I've denoted sigma. And this could take each component of the vector coming out of that linear transformation and apply the same nonlinear function in one dimension. So it might be tanh, it might be something else. Computers one often uses an operation called a ReLU, but it really doesn't matter that much as long as it's nonlinear. And then you apply another linear transformation or affine transformation, another nonlinear. So each of these is a layer, and you go through several layers like this. And it turns out that it doesn't take that many layers before you get this very broad, in some sense, universal. And there's a precise sense which is universal, even for 2 layers, but that you could arbitrarily well approximate arbitrarily closely any given function, even using 2 layers. But to do it with 2 layers, you need exponentially large dimensions in the interior. So this is standard sort of cursive dimension. But if you have multiple layers, you can often do very well without an exponential, with a reasonable size network, and that's the slightly surprising thing. So we have this big class of functions that are implemented, and then broadly speaking, there are 3 ways that they get used in machine learning. So an example of, one thing you might think you might do is you're given samples from the function. You're given a input and the corresponding output. You're given some finite list of samples, a data set, and you're now trying to learn the function that approximates or interpolates these. And so this is called supervised learning, and a basic example of that would be image recognition. You have an image, and the computer is supposed to say, is that a cat, a dog, an airplane, something else. And you regard the classification as a function. The input image, each pixel corresponds to 1 number, or perhaps 3 numbers for the different colors. So we have thousands or even millions of dimensions of this input, and now we're just getting out a very low dimensional output that typically would say the first component might be the probability that this image represents or contains a cat. The next component is the probability of a dog, and so forth. So it's going from this very high dimensional space to a low dimensional space. We're given a data set of images with labels. This one's a cat, this one's a dog. And we just do some kind of interpolation to learn a function that optimizes that. And then the interpolation is, again, almost always done by a very simple, you write down some error, such as the mean squared error with which the function realizes the data points, summed over the data points. And then you just do gradient descent. You just vary the parameters, all the matrix elements of these affine transformations theta. You vary the parameters to decrease this error function until you reach some local minimum. And that's it. That's a very general paradigm. You might wonder why it works, but that works. So there's supervised learning. There's what's sometimes called unsupervised, semi-supervised. Jan LeCun likes to call it self-supervised. You are basically just given inputs. Now you're trying to learn a probability distribution that you hypothesized that the inputs were drawn from. So, but then the rest of it is very similar. You model, you represent the probability distribution using neural networks. You minimize some sort of a cross entropy or measure of how well you've represented that distribution. And then finally, reinforcement learning. And then this is most famously in AlphaGo, AlphaZero, these programs that can learn to play games and, even from ab initio and beat, you become superhuman. And the defining thing of reinforcement learning is that whereas in the previous things, you could think of each data point as coming with a signal that, yes, here's the desired output. Yes, it did appear, so the probability must be higher there. In playing a game, you usually don't find out until the very end whether you win or lose. And then you have to work backwards and say, well, out of the hundreds of moves that I made, which ones contributed to winning and losing? So you have this credit assignment problem. So the techniques are somewhat different, but it fits within this broad sort of overview. Okay, so those are the types of general problems that have been implemented efficiently on computers. And then in practice, there's a lot of concepts and lore that go along with that. That it's learning everything from the data. It's finding patterns in the data. So it's clearly very important to assemble big data sets to make sure that they're very accurate, curate them, and so forth. There's technique such as to properly evaluate a model. You can't test it just on the ones that you trained it on because, of course, it could just memorize all the answers and get 100%. So you typically hold back some of the data set and save it to test, and then that can't be solved by memorization. And so how does it work? That you have this model that recognizes images, and now you give it a picture that was not in its training. It's never seen that picture in any sense, and it says it's a cat, and it's usually right. So in some sense, it generalized, and that's really the key theoretical problem of the machine learning. How do these models ever generalize, and why does it happen? There's clearly structure in the data sets that allow for this generalization. There's this concept of inductive bias that the model comes perhaps with some sort of a preference for functions that will generalize in some useful way. But then there's a big tension between that and my previous claim that the functions could represent any function, could approximate any function pretty well. And people honestly do not understand this in great depth. This is one of the key questions. And a thing which they do understand somewhat better is there was this, if you went 20 years ago, okay, so 2005, to a statistician and said, what do you think of these neural networks? Because the ideas go back to the 80s and 90s, and the answer you would have gotten is, well, that's a crock. That's crazy. And why is that crazy? Jan LeCun did this great work with recognizing digits in the 90s. Why not? And the answer would be, well, in statistics, we have this thing which you sometimes call Occam's razor, which says that when you make a model that fits data, you should have the fewest number of parameters possible to fit the data, because otherwise you just start fitting all the noise in the data, and you start seeing all these features that are not really there. And it's hard to even make a model that has 10 parameters that isn't just too overly general. And now you're giving me this model with 1 million parameters. And that was a valid argument. That it was actually quite subtle what's wrong with that argument, because it's wrong. The neural networks do have millions of parameters, and they do work. But it was not, it was not totally wrong to point this out as a potential flaw with the idea. And conversely, it requires explanation. Why do these models work, even having completely violated this form of Occam's razor? And so there's a concept of benign overparameterization, which contains answers to that sort of question. And then, of course, there's a lot of lore about how to make these things work, how to tune hyperparameters and choose the model and this sort of thing. So there's a great deal there. So, okay, so I was stressing the generality, and then of course that comes with a problem, which is that you learn this function, and maybe it's, again, maybe it's the central thing in your research. You want to classify manifolds or Feynman amplitudes or something, and you get this model that predicts something of interest with 99.9% accuracy, and you say, wow, that's great. So what do I learn about my function? And well, what you immediately learn is that there's some neural network that has 20 million parameters, that can fit that function. And what does it mean? And it's really very unclear what it means. And so there's this interpretability problem, which shows up in many uses. And there's a very big problem for science and math, where the whole point was to kind of understand your function. It wasn't just to fit it and get 99% accuracy. Your goal was to actually understand something. And so the 99% tells you that, well, yes, there was some structure in my data that the computer was able to somehow fit, but what is that structure? And so you're better off using a simple model if you can. There is help. There's a variety of techniques that have been developed to say which inputs, which parameters were responsible for the goodness of the prediction, simplify the model. There's a technique called symbolic regression, which is actually quite effective in physics problems, where you have the function, and now instead of fitting with this neural network, you could try to fit it with a symbolic or an algebraic expression, something written out in terms of algebraic operations, simple functions, and so forth. And then again, if you were trying to recognize cats and dogs, there's no reason to think that approach would work. But in fitting physics functions, of course, that very often does work, and there's a very, very powerful technique for that. So okay, so that's my brief summary, again, of trying to put together some of these core ideas. And now we'll talk about some of these applications. And start with machine learning as it's used in scientific computation. And I'll make that one relatively short, because I'm sure you've all heard talks about this. This is, in some sense, the most, the oldest and the most well-known of these applications. And it builds on the standard sorts of scientific computation of solving equations, solving partial differential equations, and numerical analysis and so forth. And then, technically one's basically trying to replace these existing techniques of numerical analysis and computation with machine learning models. And so, for example, you might have a weather simulation, and you might have a structural, stresses in a material, and you would start by dividing the three-dimensional space up into a grid, and perhaps having finite elements and specifying the value of the function at some discrete set of, finite set of points in that grid. And so rather than do that, you might say, I'm going to represent my function with a neural network, some sort of machine learning model. Perhaps I'll feed in the coordinates, and then the output will be the value of the function of those coordinates. And since the neural network is a general function approximator, whatever the solution is, it should be possible to represent it that way. And then instead of developing some complicated numerical method, I'll take my equation I want to solve, let's call that E equals 0, and just say, let's just look at E integrated over space, or E squared integrated over space, and that's now my error with which I've solved the equation, and we'll just minimize it the same way we minimized these other error functions in the previous discussion. And that's a perfectly valid solution technique. That's something that people did use in the past, but it's the solution technique which is automatically implemented for you in these machine learning packages with the GPUs and the CUDA and so forth. And so it's extremely efficiently implemented. You can just have a free ride on all this technological work that was done to make machine learning work well for applications, and get supercomputer power, what would have been supercomputer level computation on a laptop with a GPU. And then finally, a price you pay is that a lot of the justification of this in the machine learning context was statistical. And so it's going to be very hard, or at least going to be harder to get rigorous or even very clear error estimates out of these techniques. If you want an answer which is a good answer that you can then check in some empirical or self-consistent way, then this is very good. But it's hard to now go further in the way you can with numerical analysis and get precise error amounts. Okay, and then to be a little more specific, things that people do that work very well. So one of them is to distill the structure from a large data set of simulations. So for example, I'll just refer to work from about 5 years ago, a large set of cosmological simulations with cold dark matter that was done by a large consortium on a supercomputer. And then you can try to fit the, in particular, you could try to say what's some sort of a effective law for gravity in this cosmology, taking account the dark matter and the other dynamics on small scales. And we just get empirically by fitting the simulations. And so that you can now do by fitting the details of the simulations using machine learning, and then, for example, symbolic regression on those models that fit the details. So the first process would be called distillation, distill out the structure of the simulation and the results without, but by a model that doesn't have to really do simulations, it's just fitting functions, and then do symbolic regression to get a functional form, and that can actually produce better results than the straightforward approach. Another general technique would be to say, well, if you put your functions on a grid or finite elements, then of course there's some minimum length scale, and it's hard to get precise results on a smaller length scale. But now you could say, well, again, I'm going to do a bunch of simulations on this smaller length scale and use machine learning to learn how do simulations behave, how do my equations behave on a smaller length scale given appropriate boundary conditions, and then learn a more complicated evolution rule for the larger, or a more complicated loss function for the larger cell, and in that way model the subgrid. Now, that can be quite effective. And that's, for example, you may have had talks and read that weather forecasting has actually been significantly improved just in the last, 3, 4, 5 years doing this by a variety of machine learning, but especially the subgrid modeling. And as I understand, is you can get pretty much as accurate results, and they're comparable results, but they use far less compute if you can use machine learning to model things on small scales. And so, in particular, you can generate many more forecasts. It's probabilistic. So where before you would get 10 runs on your supercomputer to explore the possibilities, now you might do 10,000 runs on this much more efficient machine learning model and get much better sense of the uncertainties and distribution of possibilities. And again, a variety of uses where one can effectively go beyond where one was at. One which I'll build on a little bit in my next slide. I'm just going to, again, mention these things, is that there's a program to understand the Navier-Stokes equations in some detail that there's real hope that it will solve this famous Clay Millennium Prize problem of are the time evolution of the Navier-Stokes equations regular for all time, or can regular initial data evolve a singularity? And many mathematicians believe the latter, that there is some singular solution out there waiting to be found, and one can use machine learning to try to find it. And then there are tools to take such a numerical solution and actually use this as a basis of a rigorous proof of existence. And I'm working a more string theory inspired project in that same vein, using these methods. So again, just to, without going into detail, there's this important topic in string compactification of understanding the solutions to Einstein's equation and the extra dimensions. And the most famous example is the Ritchie-Flat-Kähler metric, which was proven by S.T. Yao to exist back in the 70s. So we have numerical methods for getting these, using machine learning to very, very generally to 1 fraction % accuracy, and then with Javier Gomez-Serrano, again, an expert in Navier-Stokes and the types of methods that I was just describing. We believe, and we're working on getting a rigorous reproof of at least an example of Yau's theorem, where we can prove that the Ricci-flat Kähler metric exists, say on the Fermat quintic. And if you know something about the proof, just to give the idea in 2 sentences, the proof has basically 2 components. So there's one component which is the general proof of existence, which uses, in Yau's case, what's called the continuity method. And then there's a related and slightly more general technique where you use fixed point theorem to show that, yes, my solution is close to, I rewrite the equation in the form, phi, perturbation of the Kähler metric is some functional on phi. And then if phi is sufficiently small, then that functional could be shown in general to have a fixed point, and that's the solution. And then the first point is to show in what sense does it mean, what does it mean for the function to be sufficiently small that it has a fixed point? How do you calculate all the bounds on the function that show that it's sufficiently small? And that was the very difficult part, what are called a priori estimates in Yau's theorem, and the challenge that led to him winning a well-deserved Fields Medal. And basically, we replaced that hard part with the computer calculation. We have a numerical calculation. If we can calculate enough quantities about the solution numerically and then do that in a way that can become rigorous, which, again, the short version of that is, computer calculations are not exact. They're floating point numbers. They round off. But suppose at every stage you always round up. Okay, well then you could say, yes, whatever I've computed, it may not be the exact thing, but it's some upper bound, say on the error. And so that could be a rigorous statement. And so those are the ideas that we hope to use to reprove this theorem. Okay, so that was what I'll say about the scientific computation. So, I mean, you can stop me for questions if you like, but there'll be presumably questions at the end, and so I can also move on. So I'll move on to this topic of mathematical data science. And there's a review that I cite up there from the point of view that I'm describing here. And although the slides are in this order, I'll skip ahead a bit and come back. So the basic idea is going to be intuitively very simple. There are some areas of mathematics where it's natural to produce a big data set, like knot theory. There's all these knots, back in the 19th century, people listed and made charts of knots. And you could imagine making as long a table of distinct knots as you like. Of course, it's infinite. You can never get all the knots, but 19 crossings. There is a computer database of all the knots with up to 19 crossings if you draw them in 2 dimensions. It has something like 300 million knots. And then you can have a computer look for patterns in that table. And here's an example of a well-known paper from 2021 by a group with partly at DeepMind, Alex Davies et al., and working with a mathematician and knot theorist, Marc Henneaux. So there's the table of knots. So there you can see 3 knots on the left-hand side. And then each knot has this large set of invariants that mathematicians have defined. So a famous one on the right is the Jones polynomial. There's some rules for deriving that from a knot. If 2 knots have different Jones polynomial, then you know they're different. It's a map on topological classes of knots. And it's a polynomial, but each coefficient is a number, some property of that particular knot which characterizes it. There's one called the signature. And then on the middle category there are geometric invariants. And these tend to have the flavor of take a 3-sphere, put the knot in a 3-sphere, cut out like a little tube around the knot, and then you find that the resulting surface can actually support a negative curvature, a hyperbolic metric. And then a geometric invariant might be a property of that metric, such as suppose the curvature is -1, what's the volume of that manifold? That's a well-defined question, and so that's that volume category here. The famous Chern-Simons invariant, of course, falls into this category. And so you can ask, are there relations between these many different invariants? And that's a very good question for data science and for the sort of machine learning techniques we describe. We just do supervised learning. We say, here's a big data set. Let's regard one column of this table as the output. We'll feed it all the other invariants as the input. Can it learn to predict the output given the input? And that's exactly the type of question we had on that earlier discussion. And usually the answer is, well, no. Maybe you can learn like 90%, or something. But occasionally you find that it does extremely well. And then that suggests, yes, there is some kind of a relation there, which we can try to understand. And how do we understand it? Well, if we fed in all the invariants, that's really very complicated. The first step would be to decide which of the invariants were really the significant ones contributing to that prediction. And that's what the bar graph, the bar chart on the right is expressing, something called attribution analysis, which in this case was showing that these first three invariants in this bar chart were the important ones leading to a prediction of the signature up there, this sigma symbol in here. And eventually, following all this up and working with Mark Lackenby, who could actually find counterexamples or conversely prove something that, one of these conjectures, they came up with a theorem. So this makes it an actual math paper because mathematicians, by and large, insist that you actually prove. Occasionally a conjecture is so interesting that you can publish it, but generally you need theorems in math papers, and that's what was accomplished here. So that's a successful example of mathematical data science. And then another source of big data, a place where big data sets have been accumulated is number theory. There's something called the L function in modular form database, which is even bigger than this knot theory data set. And a discovery of 3 years ago that attracted quite a lot of attention and is still being worked on is a group of mostly physicists, Yang-Hui He, who many of you will know, Q-Hwan Lee, who's a mathematician that I wrote this review with, and so forth, and two others. We're just, again, asking this same style of question. So without going into details, this is about elliptic curves in its original discovery. And there's something called an L function, which is basically assembling the number of solutions of this, in this case, cubic equation, modulo p for every possible prime p. You get this infinite series of numbers that you can assemble into what's called an L function. And so they wanted to study, again, predicting some coefficients of the L function from others. And then you start manipulating and combining the data in ways which are very natural if you're trying to just put it on a computer. And in particular, they said, let's average the nth coefficient of the L function, this APN, over a large set of elliptic curves with roughly the same complexity. There's a measure called the conductor. It's related to how big the numbers, the coefficients in the equation are, but it's a better but related measure of that. And so they just said, let's average this over all the curves with conductors, say, between 1,000 and 2,000, say. So kind of a crazy thing to do from a math point of view because these curves really don't seem to have that much to do with each other. But if you do that and you plot the average value of these coefficients, so here we've distinguished two types of elliptic curves. There's, if you know the definition, it's the rank. It's basically, are there infinite abelian subgroups of solutions? So if there are not, it's rank 0. If there are with one generator, it's rank 1 and so forth. And almost all the curves have rank 0 or 1. And so the rank 0 are blue. And you see this very nice oscillatory pattern. Each dot there is one of the curves. And you see that the average is having these interesting oscillations as a function of the p, the prime, and the opposite sign for the red. And then they showed this to mathematicians who were quite surprised. They had never even thought to look for this, and they certainly did not expect to see this. And so it was quite mystifying, and they eventually very interesting. And now we should try to prove this and see what other objects this has. So this is a real discovery made using mathematical data science. And again, just kind of if you trace through this, is explained the processes in my review, how you would be led to look at this just very naturally if you just think of this as a data science problem. So we had a workshop, a program, a 2-month program last fall at CMSA, our center at Harvard, bringing together 80 mostly mathematicians, some physicists, and building, studying, using all sorts of machine learning methods. This is an example of a application of this to Moss forms, which is another, you can either say number theoretic or spectral theory on the fundamental region in the upper half plane, and it shows similar structures. It's a general phenomenon. Okay, so that's some examples of mathematical data science, finding patterns in this mathematical data. So if there are no questions about that, I'll move on to the third of my list of 4 topics, which is search. And search can mean a variety of things, but in more precise, what the computer scientists will call it, the kind of search I'll talk about here, is a constraint satisfaction. What does that mean? And so the prototypical problem here is this, what's called satisfiability or SAT problem. So here you're talking about Boolean algebra, Boolean expressions composed with and or a not. Any number of these variables that can either be true or false, and then the 3 elementary logical operations. So you're given some potentially very complicated Boolean statement, and the problem is find an assignment of true-false values to the variables that makes the statement true, or perhaps prove that there is no such thing, which would be the unsat problem. And then this is the defining problem of this class NP, and the problem is P equivalent to NP. This is to say that it's easy to check if you're given such a solution of assignment of variables that makes it true. You can easily check, evaluate the expression and say that it's true. But it's hard to find. So there's the obvious algorithm is the one that just tries all the possibilities, makes the truth table. If there are n variables, that would take 2 to the n tries, so exponential, very slow. And although there are faster things, there's nothing that much faster. It's believed there's nothing which isn't essentially exponential like that. And so that's this claim that NP is strictly harder, or as a worst case statement is harder than P. And similarly, this problem of proving that there's no assignment, you have to find some proof, which is a little different, but this defines a class called co-NP, which is also thought to be hard. And so that's a large class of constraint satisfaction problems, and you can generalize in ways that basically keep you in the same class. The variables might have not been 2 valued, they might have had multiple but finitely many possible values. You could use other operations, you could use other functions to constrain the variables with each other and so forth, but it's this big class of problems. And then there are certain fields of mathematics where the mathematicians love to pose problems like this, and the computers are kind of naturally suited to. And for example, in graph theory, there are these famous problems, the Erdős problems. Paul Erdős, this famously eccentric mathematician, would pose problems such as this first one, which he posed. So we consider graphs with n vertices, and we're allowed to add any edges between any pair of vertices we want. And the question is, you are allowed to add edges, but never realize a 4 cycle, some series of 4 edges that comes back to where you started. What's the maximum number of edges you can have with that constraint? And if you want to challenge, go home or think about for the rest of the talk, if you had done it for triangles, there's actually a pretty easy argument that shows you what's the answer, but it's never been answered for 4 cycles. And the best solutions in general are things that you find by computer search. Another problem of this sort is called the CAPSET problem. So we're now considering n-dimensional vectors where each component is in the field with 3 elements. It's 0, 1, or 2. So we don't allow 3 vectors to add up to 0. So in some geometric sense, the 3 vectors can never be collinear. And what's the largest set of vectors with that property? So this is for reasons that I'm not quite sure of. A problem of significant interest, not just in combinatorics, but it bears on several other problems in mathematics. And again, this is a problem that it's intricate. There's clearly structure, but it's hard to kind of apply that structure. And so it's a core topic in computer science. For the purpose of this talk, rather than talk about the various methods, I'll talk about machine learning, and in particular, a method which we looked at quite a bit at our workshop. And this is now turned into something called the AlphaEvolve, which you can ask DeepMind, basically, at this point. The earlier version, FunSearch, was a joint paper of DeepMind and a mathematician, Jordan Ellenberg, which found new solutions, new best solutions to this CAPSET problem. And how did they do it? So recall, that's the problem of taking these d-dimensional vectors of field of 3 elements, element is 0, 1, or 2, and then the solution to this problem, they found a new record solution for 8 dimensions by having this fun search system write programs that would generate these sets. And what it would do is, the program is basically a function. You give it one of these vectors, and it just rates the vector. It has a single real number that comes out and says, this is a good vector, this one scores 100, this one scores 50, and so forth. And then you basically just go down the whole list from the top to the bottom, and you add the top vector first. You keep adding the vectors going down. If you ever get to a vector which would violate the constraint that 3 vectors add up to 0, you don't put that one in, but you just keep putting them in as long as you can. And so that's a way in which a relatively simple program, and here's the example that got this record-beating thing, was produced. Okay, and then how did they get these programs? Well, this is now skipping ahead, but again, I suspect everyone here has at least seen this idea that language models are good at writing programs. So what they did is they said, let's start with a simple program of the type that I just described here and feed it to the language model and say, write another program like this. And it does that. And then they give it both programs, write another one like this, et cetera. Okay, and then eventually you have enough programs that you can start evaluating and keeping only the really good ones that produce big sets, and then take some of those and say, write another program like this, and you get this sort of evolutionary process. It's a lot like this technique of a genetic algorithm or genetic search that some of you will have heard of, but this is a sort of population genetic where the mutations, the reproduction is happening through the language model. So interesting kind of machine learning application to this. So that's an example of something quite different, which again has solved these sort of intricate problems are things where this has been very effective in finding better solutions. Okay, so let me then move on to the last of these 4 general topics of interactive theorem proving. And this is one that I actually, although it has had much more impact, although not a huge, but it's a thing which is maybe not on the physicist's radar yet, but really should be. It's very much on the mathematician's radar. And so the basic question that you can ask is, what is mathematical proof? Okay, and so that's on some level a philosophical question, but of course it was a question which was in some way answered back in the turn of the early 1900s. This field of mathematical logic was created that reduced the verification of a mathematical proof if it's expressed in axioms of set theory and logical terms to a series of verifications of elementary operations where you don't need to know what the operations mean. Just if you've applied the sequence of each operation correctly, that turns into a 100% valid proof. And so that's kind of attractive for a variety of reasons, but the state-of-the-art back around 1910, there's a famous book of Bertrand Russell and Alfred Whitehead where they started developing mathematics in this type of formal way. It's called formal proof. And they got some distance, but it was just very difficult. The proof of 1 + 1 = 2, where the numbers are defined in terms of sets and logic, is 10 pages long, and things just get harder from there. So, so that was proof of principle, but not very practical. But of course, with computers, these ideas, of course, were essential input into creating computer science. With computers, we face this type of engineering question all the time. The basic instructions of the computer are assembly language, which add numbers together. They're better than 1 + 1 = 2, but compared to what the size of the computation that a program does, it's a tiny piece. But we're very good at assembling these tiny pieces into very complex programs and knowing how to check them, to debug them, to organize them. And so that type of technology has been applied to proof for, again, 50, 60 years. People have been very actively doing this, in part to try to show techniques that computer programs are correct. But they've been famously applied to a number of math theorems. So everyone here will have heard that the 4-color theorem back in the 70s was proven by a computer-assisted proof by Appel and Hawken, where the computer checked some thousands of graphs, and there's a necessary or sufficient set of conditions that will then imply the 4-color theorem for all the graphs. But in the 2000s, and in fact France was very much the center of this work, a group at INRIA, Georges Contier and collaborators, verified this four-color theorem by translating it into these formal terms on the computer using a language called coq. And so that was an example of this theorem verification. Sophisticated, the Veit-Thomson theorem from group theory. More recently, Thomas Hales proved the Kepler conjecture, this ancient Kepler's conjecture, that the most efficient way to fill space in 3 dimensions with spheres is the face-centered cube or the body-centered cubic lattices. And so he believed that, but it was proven in 1999 by Thomas Hales, again through a computer-assisted argument with hundreds of thousands of cases. And he submitted his paper to the Annals of Mathematics, and they sat on it for 2 years, and then they said, well, we don't know, you got this very complicated computer proof, it looks okay to us, but we don't know. And so he was, as a proper mathematician, was disgusted with this failure to referee his paper. And so he started a project of about 10 people called FlySpec to translate this into a language called Hull and verify. And he was able to verify his proof. So he was then convinced that he had not made a mistake. And so this technology is advancing steadily. There's a system called the lean theorem proving system, which is in its 4th version, which is now the most popular. If you followed any of these things, you'll have seen that people like Terry Tao have been using and advocating the use of lean. There's a theorem, a library. So a lot of the actually practical use of this depends on having a library that's proven a lot of the basic results that whatever your field of math or physics is that you would rely on. And the lean math lib at this point has about 1.7 million lines of code, roughly the undergraduate math curriculum, and stronger in some areas rather than others. An example. These are examples of recent successes using it. And the most famous one is the mathematician Peter Schulze, working with Dustin Clausen, have a program that they call liquid mathematics that they've been developing over the recent years. And Schulze had proven this fundamental lemma in his theory, but he had not quite convinced himself. It seemed very subtle, and so he challenged this community. Can you claim to be able to verify theorems? Verify this theorem. I would really like to know whether my argument is correct. And it took them about 3 months. A group of about 10 people, led by a man named Johan Kummerlen, who in about 3 months, we're able to check that part of the theorem that Schulze had doubts about and to confirm it. And then after about 1.5 years of work, we were able to really do it from the ground, from the axioms, from the ground up, and verify it all. So this is, I believe, the first example of a problem. So the previous things I cited were some previously existing proof that generally people agreed now being checked this way. But here was a case where the actual creator of the proof was still working on it and wanted, was not sure, was actually helped in real time by this type of analysis and verification. So it's a very promising technology. Again, mathematicians, proof is their standard. I think this, for reasons I'll get back to, will become increasingly quite important for theoretical physicists as well, but that will take a little bit more of a case. Now, why aren't all the mathematicians using it already? Okay, because you don't need AI. So far, I didn't really say anything about AI. And here's an example. Okay, here's the Pythagorean theorem written in this lean language up in that yellow square up there. Okay, so I hope you can read it. Anyways, it has this funny long name, but that was just a choice. So we have 3 points, P1, P2, P3. The distance between P1 and P3 times itself, so squared, equals the distance between P1 and P2 squared, plus the distance between P3 and P2 squared, is logically equivalent, if and only if the angle between those 3 points is pi over 2, so it's a right angle. So that's a perfectly clear and good statement of the Pythagorean theorem. Okay, and now what's the proof? Well, I'm not going to go through it in the same detail. You can see it up there. And then the basic point that the slide is making is that the proof is really not that intuitive, not that easy to either write or to read. And again, it's not like there's some mystery about it. These are lemmas that are proven that express the various components that you could assemble to make a logical proof of that statement. But you just have to learn all that terminology and learn how to put these things together. So I often describe this as the assembly language of proof. You know, that here it is a very effective thing. You can prove anything using it. There's all these amazing success stories, but you have to learn this really kind of awkward computery language, and that's the status of it. So what do you do? Okay, and well, the solution, which has been, you know, some visionaries for many years have been suggesting, is that, well, we'll get AI to write the proofs. We'll get AI to find proofs like this, and we won't have to write them. You know, we'll translate a regular proof into Lean or this type of notation. And you know, again, this field of automated theorem proving is also very old. And in fact, one of the first AI challenge problems is the theorem prover of Newell and Simon. And one could give a long talk about this, but it's again, this is one of the things I focused on since really seriously getting into these things around 2018, 2019. And in those days, reinforcement learning, like the analogy between making a proof and playing a game of solitaire. The various choices you make are like moves in this game of solitaire. And so there was some success in doing that, but there's been much more success in very recently, using large language models. So now let's you know, again, review the large language model in not detail, but at least, you know, something like what it deserves. And again, I think many of you will have seen this. I have a review on the archive from, I guess, 2 years ago that is written for physicists, mathematicians that you can look at. So you know, it's ChatGPT. So what is it doing under the hood? So these are statistical language models. The basic task is we have this sequence of words or pieces of words called tokens, and we're just given a sequence trying to predict the probability of what is the next word, what is the probability distribution over possible next words given that sequence. So it's just treating it as a statistical problem, a priori ignoring all the meaning and structure of language. And so then that puts it straight into this category of the supervised and self-supervised learning, because it's a probability distribution. It's like the self-supervised learning of the original slides. And then we use a modified neural network called a transformer that has this particular technique called attention. We train it on a huge corpus of text, in some sense all the text and perhaps even all the code on the internet, and then we use it to predict one word at a time, and then just, you know, the accuracy with which this probability distribution matches the empirical probabilities that, you know, words appear on the internet in the corpus is the loss, and you try to optimize that. And as you've all, you know, seen and perhaps experienced, these word prediction now is able to do many, many other things that you would have said required intelligence, that you can give it problems, word problems in math and physics, and it can often solve them. It can make sequences of arguments. Again, it's it really was not, it surprised everybody. It really was, in a vague sense, it was even Claude Shannon had said that, you know, if you could just predict the next word in a text, you know, you would thereby understand a lot of the structure of the language. But the degree of success of this surprised everybody. You can't even find a previous prediction literature to compare it to. And so then that's, of course, you know, ChatGPT is a couple years old now. And this had been going, the Transformer paper was 2017, so this is all relatively new. The big activity of the last year and a half in the industrial labs, which focus on this, is what they call reasoning models, trying to exactly solve word problems that require some sort of chain of reasoning more, you know, with a higher accuracy, not make stupid mistakes. And there's a lot of interesting kind of analogies, which actually did go seriously into their work. So one which is, again, many of you will have heard the idea and is worth knowing about, is a concept from cognitive psychology and behavioral economics of the dual process theory of thinking. There's this idea that human thought you can understand as being composed of sort of two systems. There's the system one and the system two. And so you see something or you hear something and you have some sort of immediate take, that's a cat, or no, you're wrong, or whatever your immediate take is. And that's the system one, your kind of immediate reaction. And it's of course very important to be able to make fast reactions, and that they're usually correct, but of course they're not always correct. And then there's a system two, which comes in when you have to do reasoning, when you have to evaluate, was that actually correct? Was that actually a well-founded judgment or so forth? Perhaps I have to solve a problem that requires a strategy. Perhaps I have to make a hypothesis and evaluate it and maybe take it back. So these are all the abilities of the system two. And then the analogy was that the original ChatGPT style of model was very good at the system one because it was just predicting each word as it came along. That was just this immediate response. And now we have to give it the system two. So that was a thing you would, these people would very explicitly tell you, a couple of years ago. There were a number of these other concepts. And the real news of the last year is that they were successful in not solving all the problems and getting the things to be as smart as humans, but successful in solving that basic problem of getting reasonably effective chains of thought that could solve more complicated problems. And there's one, again, as of a year ago, I would have said, then you got to, these people are all keeping their work secret. But what also changed around the beginning of this year was the DeepSeek model. The Chinese lab, DeepSeek, actually did publish not everything, but quite a bit about their reasoning model. And so now there's quite a bit more open work about this and a lot of interesting methods. I'll just give an example here for people that I actually use, until this year, I did not really use language models in my own work, but I now think that deep research, this thing that's available from OpenAI using their reasoning models, O1, O3, and so forth, and there are comparable things from their companies, are good enough that you can use them as research tools. It's not like they never make mistakes, but they make few enough mistakes and they have broad enough kind of capability that they really are a very useful start. And as I mentioned in the beginning of the talk, here's the paper I'm studying, here's a question I have, what are the papers that build on this in some useful way. It does give useful answers to that type of question. So it really is quite a leap forward from just a year ago. This is an example for this talk of information about the experimental search for supersymmetry, perhaps based on comparisons with string theory models, perhaps based on discoveries at a future 100 TeV proton antiproton collider, and it gave a pretty good answer. It was pretty detailed and not with obvious mistakes. And I looked for some non-obvious mistakes. A very useful summary. Again, not like the last word on the subject, but a very good first word as a summary of the topic. So it's theoretical. Yes. Well, it's not built yet, so we'll see. So. Anyways, anyways, it's making these steps forward, and this is an example of an application of language model to this problem of using the lean theorem improver that I mentioned. That this here auto-formalization refers to turning a informal mathematical text, in this case a simple multiple choice question based on this algebra problem, into the statement of the answer and the proof. And so when this benchmark of maybe 1,000 of these problems was produced back in the beginning of 2021, the best system could get maybe 20% of them right. And by the end of this graph, which was the beginning of this year, it's 60%. And I believe Google's latest Gemini model gets like 80% of these. So there's this very steady growth of the accuracy with which this is done. This is an example of, again, until this year, you could try using language models, and people did try to help doing this lean, theorem proving stuff, and they weren't that helpful. But since more or less the beginning of this year, they're actually quite helpful. And this is the start of a project to just write down the axioms of axiomatic quantum field theory. And again, this is a long project. If you know something about the, again, there are many theorems not proven yet in lean that you would need to really get this thing down to the foundations. But rather than getting stuck with the help of, in this case, O3, it's kind of more systematic. One can find the missing points in these definitions, which are not that easy to guess. Again, if you look at this is getting up as far as defining a quantum field theory as a probability measure on field space, and then starting to define the observables that would get into the action. Okay, this is the more or less state-of-the-art dedicated systems to this. There was this famous last summer result of, there's the International Mathematical Olympiad, and there's the AI International Mathematical Olympiad. And DeepMind last summer was able to produce a system called Alpha Proof, which in some sense almost got a gold medal. If you took its answers, again, it didn't play by quite the same rules, but it did play by the same basic rules that you gave it the same problem statement as the human competitors. In this case, you gave it something like 3 days to do the problems instead of 1 day. But it was able to solve something like 4 out of 6 totally and partially another one, and came close to what would have been the gold medal. And it's been reliably reported that both they and another group have a system that will get a gold medal on this year's. They expect to get a gold medal on this year's IMO, which will be next month. So this is the state of the art of this. Okay, so let me come back now to this kind of trying to say something about the future. And this is the graph that I started with about the progress in AI. And then basically this, in terms of AI, what are these red dots? These are benchmarks like the one that I described for the formalization of mathematics, but 1,000 benchmarks on the site of papers with code. There are these various leaderboards where people submit their model and get an evaluation. What accuracy did the model get? And then you more or less just combine the results from these 1,000 benchmarks, very analogous to the way that you might combine stocks into a stock index. And that's what this series of red dots is. It's the accuracy ratings of 1,000 benchmarks combined according to a systematic rule. And now you see this pretty steady improvement, which you can check is about doubling of performance every 2.5 to 3 years. And not quite as fast as Moore's law, but pretty fast. The orange and the blue lines there are numbers of patents and papers. This was done by an economist, and these are, of course, more traditional measures. They also grow exponentially, but more slowly. And what's that green series of dots? Well, that green series of dots actually comes from computer chess. And so it's interesting, of course, now we'll come back, and we're heading towards this sort of question, what would it mean for a computer to reach a sort of human intelligence? And of course, well, intelligence at doing what? And which human? I mean, humans have this vast range of abilities, from the top people down, all the way down. And a field where people have put a lot of effort into measuring and characterizing this very broad range of human abilities is, of course, chess, where we have these systematic ratings. We have what's called the ELO rating system, which is based on pairwise comparisons. Basically, you try to predict, given players A and B, what's the probability that player A will beat player B. And to briefly, to summarize, a 400-point difference in these ELO ratings is about a 2 sigma difference in this probability distribution, from being evenly matched to, say, 95% chance that the one will beat the other. And then this comes from a 10-year-old, the Wikipedia list of numbers of players at the various FIDE ranking scales, from sort of beginning master, playing in tournaments, perhaps winning lesser tournaments, all the way up to the top players, Magnus Carlsen and so forth. So this range of about 600. Okay, so you can do this, obviously, these ratings for computer chess engines, and in particular, the Swedish Computer Chess Association has been doing this since the mid-'80s, and that's what this green series of dots is. That time series goes back to the mid-'80s, and that's the ELO rating. And now it's a slightly different scale. It's actually a linear increase in the ELO. It's about 54 points per year, very steady, except for this blip around 2008, where we believe they bought a much better computer that year. But it's on a kind of normal size computer. It's not like a Deep Blue, in 1997, which was on this purpose, special built supercomputer. And in any case, you can actually, if you look at the definitions, it does make sense to put these things on the same scale. You could think of the benchmarks as being very much like tournaments, where what's the probability that the agent or the computer will solve a given benchmark question. The two things do belong on the same scale. And then the intriguing observation that surprised us, and we can't really explain, is that these two lines have the same slope. So the intercept is arbitrary. You just say there's some starting point, but the slope is meaningful, and the fact that the red line and the green line have the same slope, both of them, the ability is doubling every 2.5 to 3 years. And then it was this 40-year long time series in the case of chess, and well before machine learning. So it's quite intriguing. And then what we can take from that is that we can now look at the history of computer chess and use this as a guide for progress in AI, because this progress is really very similar. And you might try to make other analogies between doing math and physics and so forth and playing chess. And it's true, there's some analogies between them, but I certainly wouldn't try to make very much of those analogies. There's lots of differences between them, but that's not the argument I'm about to make. I'm about to tell you that the rate of progress seen empirically is roughly the same. And so what happened in chess? Well, in chess we went from, again, the early 90s, when computers were at this kind of roughly 2,200 playing and sometimes being masters, through 10, 12 years later, when they were reliably beating the international grandmasters. So that corresponds to this 54 points per year increase. And then we've looked at this series of 1,000 benchmarks, including doing math problems, doing physics problems, and so forth. And on a very broad average sense, the rate of progress is the same. And so from that, it seems like a reasonable prediction that the future AI progress, if at some point in time you were willing to say, yes, the ability of an AI to do math, to do some other difficult thing, is at the top level here, a candidate master, which you can kind of guess. It's maybe this AI research assistant, which I'll talk about a bit more in the talk. Maybe it's some sort of graduate student level, somebody who shows promise but is just at the beginning of their career. Then successively through these lines on the graph every 2 years or so, and roughly 10 years later at that level of the top humans. So that's the prediction that this question, or?
So how much do you think is due to increasing computational?
Oh yeah, quite a bit. Exactly. The biggest contributor to this is increasing computation. So now you could ask, do we expect, so that's a factor. Another factor is algorithmic improvement, that the algorithms get better. Another factor is just energy has to go in, the resources you need. That's right. So definitely, to predict that this will happen over the next 10 years, you need to believe that those factors will all continue to have input. And people have exactly asked that for these other applications of AI, of using it to solve more practical things of value. And that's the general statement, is that if people do build new power plants and kind of continue on the path that they're talking about now, it will continue for the next 10 years. Yes, that's right. That would be an assumption in any such prediction.
Would it be interesting to divide by flops?
Yeah, you can look at our paper. We have take a look at our paper, because we do talk about what questions behind it like this. Yes. Okay, so this prediction. So again, now we can come back and combine Sam Altman plus some reasonable extrapolation of what I was showing you to say that perhaps in even as little as 2 or 3 years, the computers will be useful assistants. You know, they'll be writing this kind of theorem-proving lean code. They'll be you know, helping us to code our programs. They'll be doing literature searches. They'll be, you know, very helpful to the point where we all, you know, find them quite useful, but not so strong as to really be doing research in any way on their own. And that seems like a very plausible, to me, prediction over the next 2 or 3 years. And then 10 years later, we would have this progression to top human ability, and then presumably beyond that. Now, it's possible there's evidence that things are happening even faster now. And this is another actually interesting comparable thing, is that there's a sort of a tournament for language models called the chatbot arena. And you can just go to this online. And how does this work? You know, so you go to this website. You can ask a question the way you would ask it to a language model. And what it does is it gives it to 2. It randomly picks 2 language models, A and B. And then it gives you back both answers, A and B, and then it asks you which answer was better, A or B. And you can rate it. You can say, yes, I thought A was better. And then A wins that tournament. And then it just, you know, does that with its, you know, millions of questions that hundreds of thousands of people are asking, and assembles an ELO rating, very analogous to the chess ELO rating. And then this is the recent progress, because this is only like 2.5 years old. This is the recent progress. And the actual, again, the intercept here, the specific number is not meaningful, but the slope is on the same scale as the previous things. And this guy is going about twice as fast, 100 points a year. And so now you could debate, has this progress really sped up to double what it was? And there are people that sort of think that and would say, yes, you know, language models and AI are helping us write code and helping us, you know, and speeding up the progress. But it's only 2 years, you know, you know, who can say? And you can also make arguments, which I'll come back to, against that claim that things are speeding up. So, okay, I have, I think, 15 more minutes. So let's say a bit about what we might hope for from these research assistants. Again, you know, coming back to these early days of AI, and these were not, you know, these proposals were made quite a while ago. I worked with one of the pioneers of AI named Jerry Sussman back in the 80s, and he was very into celestial mechanics. He was a computer scientist, but we built a computer together called the Digital Orrery that did celestial mechanics. And he wanted to make an AI assistant for problems in dynamics, the dynamicist workbench, which would conduct numerical experiments using, you know, ODE or Hamiltonian mechanics, map out the phase space, find the relevant structures and so forth. And again, in 1987, this was quite futuristic. And we're not there yet. We don't even have that yet. But this is the sort of thing that you could imagine as just now coming into range. And so I think the idea that it's, you know, clearly the idea that it's just like a human collaborator is not really the idea you should have in mind. You know, obviously, a computer assistant will have many advantages and things, such as doing the computer part of the project. You know, doing the coding, doing the debugging, searching through, you know, huge databases, searching through the huge literature, you know, and so forth. It has, you know, I think it will become important, this ability to verify. I mean, this is not a point that I made a slide for, but let me just say it that. As I'm sure everybody knows, one of the great weaknesses, and still somewhat a weakness in these language models, is this tendency to so-called hallucinate, to make up a fact. And, you know, making up a fact is not such a bad thing, but then to be totally convinced that this is really a fact, you know, that I, you know, as if I read this someplace, and it makes up citations, it makes up this and that, and, you know, again, it used to do this, you know, the first ChatGPT did this to the point where it was pretty useless for doing math and physics, and something like deep research obviously is much more attuned to looking at the actual literature that is the source for what you're doing, but it still makes this kind of a mistake. And on the other hand, we have this interactive theorem proving, which is very hard to make anything work, but once it works, it's logically 100% correct. You know, it verified it, and totally logical. So it's obviously this kind of a natural combination to make the language model produce code and theorem proofs that can be 100% verified, and together these things will very likely. This is exactly the direction that many people are trying to pursue now. That again, not for even most applications that people imagine doing for AI, but for math and physics, a very, very potentially very powerful set of techniques. This is a slide talking about the many aspects of, again, both, anything in the mathematical sciences. I'm treating, math and physics very similarly, although there are differences. And there are many aspects of the way that we think about our problems which are not strictly encoded in logic. And to some extent, some of them you could encode. You could say, yes, to solve this problem, you follow this series of steps. It's kind of like a program. But of course, we don't tend to do that. A language model might not do it that way either. It might, do the reasoning informally. Okay, this is this point about, the importance of reliability, the hallucinations. If there's an error rate, that directly limits the length of the kind of arguments you can make. So even if we're at the point where they're 95% accurate, which seems like a reasonable, back of the envelope number, then you can make a 20-step argument with some reasonable probability of success, but you can't make a 40-step argument. So you basically need not just low error rates, you need to properly distinguish when something is actually proven and when it's not proven. That's what allows you to make very long arguments. Yeah.
I mean, we talk about error rates because the model hallucinates and sometimes says wrong things, but you see no opportunity for the model to say at some point, I don't know.
Oh yeah, for sure. That's right. That's a perfectly valid thing. That's right. It should distinguish things for which it knows and which it doesn't know. So indeed, that's the real cue. Obviously, most questions that you get asked, and certainly most research questions, the honest answer is, I don't know. Right. That's right. And indeed, the model should work with facts on that way. It should work with attributions and proofs. Indeed, I myself think that this is a thing that a topic that people don't try to put enough, as much as they should, into this discussion. But there's certainly nothing stopping the model from representing that as well. Okay, this is a work from Google, basically applying to biomedical research and assist as an example of the sort of thing that you could imagine. This is an example of, I talk to people trying to develop ideas. So in any real project, research paper, you're working on many different levels. You would have a conceptual explanation. You would have the actual framework, say physical laws or whatever scheme that you're working within. There's the narrative of what you're actually doing and trying to show in that paper. There's the detailed computations to do it and so forth. There might be data. And then if you look at the actual papers, they very much emphasize number 3 over all the other things. They generally make references, for 1 and 2 and say, look at that book, or, as everybody knows, and then they give enough of, the computations for somebody to follow if they're willing to do some work. And that may be as it should be. But again, if you step back, again, you would say, well, really, a task for an assistant would be to make sure that the discussion is consistent on all of these levels, and to say, well, yes, your narrative all sounds very good, but in the textbook it said that, which is different, again, so this type of translation, translating from text to code is something that seems to be much easier than many other tasks, and this has turned a sizable amount of the work in getting a project to cohere into problems of translation. So I think that might be a valuable way to think about it. Okay, so now let me, as the last of these topics of what AI has not really done yet, and if you're looking for arguments against these very futuristic or optimistic claims, I think it's really fair to say that, well, if a computer is really going to be superhuman at doing math and physics, then it will surely be discovering things. And so what's the simple discovery that it makes today that you can say will now become, in 10 years will make a great discovery? And I think if you look at the papers that claim to do this, by and large, the computers have not really made discoveries. And what it really is doing is people are taking some part of the problem and basically giving the computer, in some sense, a pre-defined or pre-digested problem. Just to give an example, you might fit a data set of force laws and some sort of, or trying to fit the dynamics of celestial mechanics and say, yes, I've fit the inverse square law of gravity, therefore I have discovered Newton's law. And well, compared to what Newton actually did, this is really epsilon, to identify that exponent too, out of the whole framework, it made sense to do any of this stuff and to pose this question and to develop this, all this structure. And at the very least, the computer should come up with the line of examination that leads to checking these various hypotheses. And then once it comes up with one, it should at least have some reason to say, oh yes, here I've confirmed this hypothesis and that's why it's interesting. And so there should be some kind of, again, something, the way it's been stated in really almost all the literature is somewhat subjective, but to call something a discovery, it doesn't have to understand it, I would say, at the level that a human could deeply understand something, but it should show something which corresponds to understanding the discovery. And then I think the real, again, one reason this is hard to study is that if you try to do it with language models, of course, you already fed them all of our present knowledge. The only really fair test there is it's got to discover something new that humans didn't discover, or else who knows whether it got it out of its training data. Now you can imagine the thought experiment that would answer this question. Suppose you could train it exactly on all the mathematics up to the year 1800. Well, then we know the central and important discoveries that came after that. Could it discover Galois theory? Could it discover group theory and so forth? So, I mean, these would be very fascinating experiments that, in principle, you could try to do with a language model. I mean, this will be getting at this notion. You can phrase much simpler problems of that sort. So this is what, to my mind, the study and the development of the ability of computers to do autonomous mathematical discovery, to discover things that weren't just fed into its training data, or simple things that are simple given the framework that's been given to it. So David McAllister, one of the early pioneers in this, who does machine learning now, but his thesis was on this topic. He has been for many years developing a system he calls math zero by analogy, well, more or less since alpha zero. This is the analogy of starting ab initio with only set theory and logic. How much of mathematics could you discover? I have a whole talk about this that I've given, for example, in Cambridge, UK, that you can find online, this type of question. So this is the reductio absurdum, that you can actually write a simple program that generates all possible proofs. And so in that sense, you can generate all provable statements. But of course, that's not doing mathematics. It has an incredibly tiny fraction of interesting statements. The challenge is to pick out the interesting statements. And there were interesting papers from the 90s that did this sort of thing, that made interesting conjectures, in a survey paper that explains the heuristics that it used to try to pick out the interesting ones. And so there's something there to work from. But again, very, very much in its infancy, this kind of study. And I would tend to agree. Without this, it's hard to make any totally believable prediction about the futures of AI doing mathematics and physics, and that this is also another missing element. But I would also tend to believe that this is not going to be an obstacle either. This may not even be that much harder than the things that we've done already, but it does deserve more attention. I guess this is more comments on this sort. So for example, it may be that you need to train the language model on tasks that are much more similar to discovery instead of training it just on solving problems. So that's my survey. And let me briefly, again, conclude that I think we have seen many, and I've shown you many examples of machine learning and related technologies, very useful for math and physics research, but really evolutionary, incremental progress, especially when you see that revolutionary progress is possible. AlphaFold was revolutionary in its own field, but we haven't seen that yet. Similarly, there's a lot of potential. The system like Lean has huge potential for not just verifying proofs, but for example, allowing collaboration. Many people can try to contribute to the same proof, and in that case, the bottleneck tends to be how do we convince that each person's contributions, when we don't know all those people, is correct? Well, now this allows you to solve that bottleneck, and you can have much larger collaborative projects. But as things stand, it's quite hard to use, to learn to use, and to use Lean. But despite this sort of incremental state of the art, since the progress continues to be exponential, this is, again, just a preview of what we're going to see over the coming years. As was asked, well, you should try to analyze the presupposition that progress, the inputs for the progress will be supplied in the way that they need to be. But you can find such analyses out there, and certainly for the next few years, perhaps the next 10 years, people are pretty confident that this can continue. I think we're close enough to many of these abilities that the math assistant would have to say it's quite reasonable that within 2 or 3 years we will have. And in fact, again, the language model, just as of this year, starts to be something that you might call a useful assistant, carrying out some of the tasks that we would want to do well enough to make it really worth our time. And more of the tasks over the next year or two. And then I argued that by this quantitative analogy of the similar growth rate with chess and with other AI topics, the transition from this kind of beginner but useful ability to solve, to carry out the task, to the top human abilities can happen over about 10 years. And although it's hard to believe, it seems like a fairly quantitative and reasonable argument. And so it is something that we all have to come to terms with and think how it will affect our work and our careers. But I think, again, in general, although there's obviously a lot of potential for disruption and danger in this, at least for research, I think the attitude we should take is that if we're going to get these much more powerful tools to help us, then we should just become that much more ambitious. We really should start trying to think about problems that clearly would have been too hard, without this sort of thing. And now maybe we have a shot at doing them. So that's the message that I'll leave you with. Thanks.